heat always passes from a warmer body to a colder body. In other words, it never goes the other way around. This simple process has been observed by humans since prehistoric times. But in 1850, a German physics professor discovered that this basic assumption leads to one of the most profound laws in all of science. A law that governs everything from how particles behave to how the sun powers life on Earth, all the way back to the beginning of the universe. This video was sponsored by KiwiCo. More about them later. Thermodynamics, the science of heat and motion. Most of us today are familiar with how scientific theories can lead to remarkable applications. Much of our modern technology relies heavily on quantum mechanics, Maxwell's electromagnetic theory, and Einstein's theory of relativity. But for thermodynamics, the influence was the other way around. Technological applications are what led to the scientific theory. And the original catalyst for this development was a simple yet serious practical problem. Suppose you're operating a mine and at some point hit water. What's the easiest, most efficient way you can extract the water to allow the mine to continue operating? This question was on the minds of many people in Britain in the early 1700s. You see, around 300 years ago, Britain was a global leader in coal production. In 1700, it produced 80% of Europe's coal. And at the same time, it was also experiencing a significant population boom. The rising population created such a demand for coal that the mining industry struggled to keep up. The risk of mines flooding was a constant threat. An inefficient means of pumping water out left deeper and more plentiful reserves completely untouched. The situation would dramatically change, though, due to an invention by an Englishman named Thomas Newcomen. A Baptist preacher who was also an ironmonger, Newcomen invented the world's first practical steam engine. And he created it specifically to deal with the issue of water in mines. The Newcomen engine consisted of essentially three main parts: the steam engine, the beam, and the pump. The steam engine consisted of a wood or coal fire at the bottom. Just above it was a tank of water that would be brought to a boil by the fire underneath. Above this tank, there was a cylinder equipped with a piston. The tank of boiling water connected to the cylinder by means of a valve. When the valve was open, hot steam would enter the cylinder and push the piston up. Once the piston was fully raised, the valve was then closed and the cylinder became sealed. Attached to the cylinder was another valve connected to an entirely separate tank of cold water. This valve would then open and cold water sprayed into the cylinder. The cold spray caused the steam to decrease in temperature and transition from a gas into a liquid. And as it condensed, the amount of pressure inside pushing on the walls of the cylinder dramatically went down. As a result, a vacuum was created. The atmospheric pressure from above then pushed down on the piston, which lifted the pump up, drawing water from the mine in the process. A third valve was connected to the cylinder, and it opened at this stage to allow the condensate to be flushed out. At the same time, the middle valve connected to the boiling water was opened again, eliminating the vacuum and allowing the entire process to repeat. The Newcomen engine drastically changed the British coal industry. By the mid-1700s, hundreds of these engines were placed throughout British mines. And by 1830, Britain was producing more than 30 million tons of coal each year, up from just 3 million in the early 1700s. But this dramatic uptick wasn't solely due to the Newcomen engine. In fact, there was a serious problem with the original steam engine that led to an ingenious improvement on it: the problem of latent heat. The concept of latent heat was first discovered and explained by a Scottish scientist named Joseph Black. Black found that when adding just a bit of heat to water, the temperature would typically rise quickly. However, something different happened once the water reached its boiling point. At about 100 degrees, he found that as he added more and more heat, the temperature didn't change at all. He reasoned that all the additional heat energy must have been going into turning the water into steam. So Black discovered that heat could affect an object in different ways. It could raise its temperature, or it could cause it to change from one phase to another. This latter effect he called latent heat. And the amount of latent heat needed to turn liquid water into a gas was enormous, which is exactly what Newcomen's engine did. But the engine was also incredibly inefficient. It wasted most of this heat energy. In fact, it only used less than 1% of the energy that was produced by the burning coal. The reason was because of how the piston and cylinder operated together. With each cycle, the gas molecules had to be cooled down and condensed. Since this happened inside the cylinder, the metal had to be cooled down as well. And then later in the cycle, more energy had to be used to again heat everything back up. A solution to this problem was found in 1765 by a Scottish scientist named James Watt. Watt realized that Newcomen's engine could be greatly improved if one could figure out how to keep the cylinder hot so that it didn't require reheating, and at the same time condense the steam and create the needed vacuum for the piston to work. His invention was ingenious. He decided to add a second cylinder to the setup, one that would function as a condenser. This cylinder would remain cool, and it would be used to condense the steam. So the condensation no longer occurred where the piston operated. Instead, once the piston was fully raised, the steam would be vented out into the second cylinder. The condensation occurred here, and then it drained out through a valve on the other end. Watt also found that if the initial pressure was high enough, he could cut off the supply of steam early, and the steam in the cylinder would still push the piston to the end of its stroke. He even found a way to return some of this steam back to the boiling tank towards the end of the stroke here. Once the pressure was equal to the atmospheric pressure, then a valve would open to the condenser. Watt found a way to make the steam engine much more efficient. Though his engine was still only about 5% efficient, it was about 15 times as efficient as the Newcomen engine. This improvement in efficiency played a significant role in accelerating the Industrial Revolution. But could Watt's invention be improved? Just how much more efficient could the steam engine possibly get? Though the applications were apparent everywhere, and there were other moderate improvements to Watt's design, the ultimate answer to these questions and the theoretical understanding of thermal efficiency would take another 60 years or so to be resolved. The resolution would occur in 1824 when a young French scientist named Sadi Carnot laid the foundations of a new science, thermodynamics. And the best way to learn about a new science is, of course, through hands-on experiments, which is why I love KiwiCo, a company that makes fun, educational, and inspiring STEAM projects for kids. My 4-year-old daughter loves these and jumps at the opportunity to build something together with me whenever I pull one of these crates out. With KiwiCo crates, kids can learn science, technology, engineering, art, and math concepts through interactive, play-based building projects. The best part, all the materials you need come right in the box. So you can just open it up and get started right away. KiwiCo makes crates for kids of all ages. 8 different subscription lines for various age groups from newborns all the way to adults. This particular kinetic light-up speaker crate I have for ages 12 plus is a bit more complex, and it dives into the science of circuitry and sound. I had a ton of fun wiring up the machine and building a cool toy that I can continue to enjoy. Having fun, building something yourself, and learning interesting concepts along the way, this really is the best way to learn. If you want to try out KiwiCo yourself or inspire in your kids a love of learning STEAM concepts, just go to kiwico.com/abide or click on the link down below and get 50% off your first monthly crate. Thank you to KiwiCo for sponsoring this video, and now back to Carnot. Born in 1796, Carnot entered the École Polytechnique in 1812. A school founded in 1794 where students underwent military training while at the same time specializing in studying science and engineering. To say that the school was associated with some of the greatest scientists of the time is a gross understatement. Joseph Louis Lagrange, Pierre-Simon Laplace, and Joseph Fourier were just some of its first professors. And Carnot received instruction from Ampère, Coriolis, and Poisson, names that are found all over the place in physics and engineering textbooks today. Carnot's father, Lazare, was also a great mathematician and one of Napoleon's greatest generals. Sadi followed in his father's footsteps and began a military career as well while studying at the École Polytechnique. But a few years after Napoleon's abdication in 1814, Sadi Carnot retired from his military duties and decided he could serve France in a better way, by studying heat. It was clear to him that France's future military and industrial success depended on its ability to improve its steam engine technology. Years of study would culminate in the only book he ever published, a 118-page work of genius titled Reflections on the Motive Power of Fire, published in 1824. He begins this work by noting the societal importance of heat. Everyone knows that heat can produce motion, that it possesses vast motive power no one can doubt. In these days, when the steam engine is everywhere so well known, the study of these engines is of the greatest interest. Their importance is enormous, and they seem destined to produce a great revolution in the civilized world. After continuing in this fashion and discussing the history of the engine, plus its importance to Britain, he sets the stage for what he aims to do with this work. Notwithstanding the work of all kinds done by steam engines, their theory is very little understood, and the attempts to improve them are still directed almost by chance. It is necessary to establish principles applicable not only to steam engines, but to any imaginable heat engines. He then goes on to brilliantly describe the physics of how an ideal heat engine would work. Begin with a cylinder and piston filled with air at some temperature T. Next, imagine you had two objects which always maintain a constant temperature. We'll call one the hot body and the other the cold body. Now, the temperature of the air inside the cylinder is just below T1. So when the hot body is placed in contact with it, heat flows into the cylinder. This causes the air to expand in order to maintain its temperature. Next, we remove the hot body, and at this stage, the air continues to expand. Without heat flowing in, though, the temperature of the air decreases until it reaches the temperature of the cold body. The cold body is then brought into contact with the cylinder, and the piston pushes down. As a result, the air is compressed and heat gets transferred into the cold body. The cold body is then removed, and the piston continues to push down, which raises the temperature of the air until it's just below T1. The hot body is then added again, and the entire process can repeat. The key principle underlying all of this analysis is that heat always passes from a warmer body to a colder body. In Carnot's analysis, heat was a sort of weightless fluid called caloric, and its tendency to move in this very specific way allowed it to be utilized to do useful work. Carnot further found that in order to make a heat engine more efficient, all you had to do was to increase the temperature difference between the hot body and the cold body. And the efficiency could be described by this equation. So a 100% efficient engine could only be achieved in the limit that the hot body went to infinity or the cold body went down to absolute zero. With his publication, Carnot had just created a whole new branch of theoretical physics, thermodynamics, the study of heat and motion. But this went completely unnoticed at first. As one author described it, Carnot's reflections had been received by the official world of science in utter silence. The only person who kept the memory of Carnot's results alive was Émile Clapeyron. Clapeyron was a French scientist who was deeply indebted to the work of Carnot. In 1834, he published his own work titled Memoir on the Motive Power of Heat, where he derived many of the same results as Carnot, but in a much clearer, more rigorous, and analytical fashion. He was also the first person to describe Carnot's heat engine graphically. In 1843, this paper would be translated into German by a scientist named Johann Poggendorff. The translation would eventually get into the hands of another German scientist named Rudolf Clausius, who would develop Carnot and Clapeyron's work further, finally arriving at the second law of thermodynamics. Clausius was born in 1822 in Pomerania. When he was 16, he went off to the University of Berlin to study math and physics. At the age of 28, he became a professor, first in Berlin, then at a new technology institute in Zurich, Switzerland. In 1850, he decided to write his own analysis of heat. There was one fundamental disagreement that he had with Carnot. As Clausius describes the disagreement, he says expressly that no heat is lost in the process, but that the quantity of heat remains unchanged. I'm not aware, however, that it has been sufficiently proved by experiment. In other words, Carnot believed that heat must be conserved. Clausius was not convinced, and he gave a couple reasons why. First, heat could seemingly be increased, as for example when it is produced by friction. Secondly, there was growing evidence that heat was not a fluid, but instead that it consisted of the motion of small particles. This new framework made it much easier to conceive of how heat could possibly be transferred into mechanical work. Clausius then says that these facts compel us to accept the equivalence of heat and work, on the modified hypothesis that the accomplishment of work requires not merely a change in the distribution of heat, but also an actual consumption of heat. So heat can be converted into work, and work can be converted into heat. He then went on to give this principle of equivalence between heat and work a mathematical form, which we now know as the first law of thermodynamics. In other words, heat is not conserved, but energy is. Then in 1854, Clausius wrote another work, where this time he focused his analysis on what he called Carnot's theorem, that heat engines work because heat always flows from a warmer body to a colder body, with the amount of heat transfer depending on the temperature difference. To Clausius, this theorem was incomplete, and it was totally unclear how it related to the first law he discovered earlier. The dilemma would be cleared up though when he focused on Clapeyron's graphical representation of Carnot's ideal engine, and on the fact that it was reversible. Put simply, when you went in one direction, work would be produced by heat. If you reverse the process, heat would be produced by work. He wanted a mathematical description of this equivalence, and he found one in what he would call the theorem of the equivalence of transformations. In his words, if two transformations which, without necessitating any other permanent change, can mutually replace one another, be called equivalent, then the generation of the quantity of heat Q of the temperature T from work has the equivalence value Q over T. And the passage of the quantity of heat Q from the temperature T1 to the temperature T2 has the equivalent value Q times this expression. He then considered a bunch of different bodies at various temperatures and summed all the equivalence values, which in general could become an integral. For a reversible process, he showed that this value must equal 0. The reason is because if it was less than 0, then this equation would also have to be less than 0 for some part of it. But if that were the case, then that would mean that heat could flow from a cold body to a warmer body, which shouldn't be possible. And if this value was greater than 0, then you can simply reverse the process and arrive at the same conclusion. So the only possibility is that this value must be 0. But what about the case when this process is not reversible? Well, it couldn't possibly be negative for the same reasons, but it could be positive. He summarized his findings by saying the whole mechanical theory of heat rests on two fundamental theorems, that of equivalence of heat and work, and that of equivalence of transformations. Believe it or not, this is the first appearance of the second law of thermodynamics, and he deduced it from the principle we began the video with, that heat cannot pass from a colder body into a warmer body. About a decade later, in 1865, Clausius would write another paper. In it, he slightly modified his second law and finally introduced the concept of entropy as a measure of irreversible heat loss. This paper contained his most developed version of thermodynamics. He finally declared that the entropy of a system can never decrease. And he would conclude the paper by writing a 2-line summary of his laws of thermodynamics. The energy of the universe is constant, and the entropy of the universe tends to a maximum. Thank you to all my generous patrons who pay me to decrease the entropy of learning physics and math. If you'd like to join them and support the channel, click right here.